discuss the norm space, Banach space, the definitions and some fundamental results. To go in deep, to get a bit more deeper results, we require some basic fundamental results, theorems. There are 4 fundamental theorems which are very much useful in developing the theory of norm as well as the Banach spaces. These theorems are Hahn-Banach theorem, Hahn-Banach theorem, which is basically an extension theorem, an extension theorem for linear functionals on vector spaces. In fact, what we do is we are interested to extend the linear functional from a sub vector space to the larger class of the vector. If we have say Z is a vector subspace of X and f be a linear functional defined on Z which satisfies certain property or certain conditions are satisfied by the function f, may be dominated by another function, some sublinear function or something by f, then the Hahn-Banach theorem gives you a guarantee that it can be extended to the entire class X without losing the property. That is, the extended functional f delta will also remain linear as well as it will retain the same condition which the function f has over Z. Okay. So, this is a Hahn-Banach theorem, we will go in detail. Then another results is uniform boundedness theorem. This theorem is given by Banach and Stenhouse. Banach and Stenhouse is also known as the Banach-Stenhouse theorem, and this theorem gives the condition. This theorem gives conditions sufficient for the sequence of norm T n to be bounded. Where the T n's are the bounded linear operators from a Banach space X to a norm space, Banach space into a norm space say Y. This is a Banach space and this one is the norm space, and this is a bounded linear operators. So, this result basically gives you the sufficient condition when the norm of T n to be bounded. In fact, what is to be shown in this case is, if T n be a sequence of the bounded linear operator from a Banach space X to a norm space Y, which is pointwise bounded convergent, then a sufficient condition is obtained by this theorem in the uniform boundedness theorem by the Banach and Stenhouse, so that the norm of sequence T n becomes bounded. So, under what sufficient condition the T n becomes uniformly bounded. So, that is why it is also known as the uniform boundedness theorem, and this theorem has a tremendous application. Its applications one can see in the summability theory, in the Fourier series, summability theory, in Fourier analysis or Fourier series, we can go for this application. Then weak convergence and strong convergence. In this also we can see the uniform boundariness theorem has a tremendous application. Similarly, Hahn-Banach theorem gives you the guarantee that norm spaces are sufficiently enriched with the linear functional, so that one can get the concept of the dual very quickly. Okay, concept. So, third one is that open mapping theorem. Open mapping theorem. This theorem states that bounded linear operator T from Banach space to Banach space is an open mapping. This theorem says that bounded linear operator T from x to y, a bounded linear operator from the Banach space x and y. Okay, from a Banach space x to a Banach space y is an open mapping. That is, it will send the open sets to open set. That is, T sends open sets to open sets. So, when the T sends the open set to open set, it means if T is bijective, then T inverse will be continuous. So, that is, if hence if T is bijective, then T inverse is continuous. Why? Because we know this mapping T, because the T is continuous if and only if inverse image of this, if implies inverse image open set G is open, where G is open. So, if the T which sends the open set to open set, it means if T is a 1 1 on 2 mapping, then the inverse operator T inverse will also remain continuous. So, in case of this open mapping theorem, we can. Now, and fourth one, we have the closed graph theorem. Closed graph theorem that says that this gives a condition under which a closed linear operator is bounded. Now, when we say is a closed linear operator means an operator in which the graph of the operator graph is closed. So, we define the closed linear operator as the operator T is called the closed linear if the graph of T is closed. So, operator is closed linear operator. Closed linear means T, a linear operator means a linear operator T from the domain dt, which is a subset of x to y, these are norm spaces, is closed if its graph that is g of t, zeta of t, the set of x y such that x belongs to the domain of t and y is t x. This graph is closed in the norm space x cross y. X cross y, x y are norm space and T V linear operator domain D is called them. And when we say x and y both are under which a closed linear operator T from x to y both are Banach spaces, both are Banach spaces, x and y Banach space, then T from x to y or dt of subset of x to y, if it is a closed linear operator, then the operator T is bounded. That is what closed graph theorem says. Is a closed operator if and only if it is closed and the operator is bounded. Okay. So, we have these 4 theorems, and this theorem has a tremendous application in the development of the functional analysis, and many results can be obtained quickly by application by using this one of this theorem which is required. Now, we will go in detail and see the one by one Hahn-Banach theorem, uniform boundedness theorem, then open mapping theorem and closed graph. First the Hahn-Banach theorem, we will see the proof, and then what are the how the Hahn-Banach theorem can be applied, can be used to get the other results quickly rather than follow classical way of proving the results. Okay. So, in order to start with the Hahn-Banach theorem, or in order to develop proof for the Hahn-Banach theorem, we require the concept of the Jones lemma and the related partially ordered set, maximum, minima and so on. So, first let us see what is the partially ordered set, and then we go for this Jones lemma, and finally, for the proof for this Hahn-Banach theorem. So, partially ordered set, partially ordered set. Okay. A partially ordered set, a partially ordered set, a partially ordered set is a set M on which there is defined a partial ordering. Partial ordering, that is, what is the partial ordering? That is a relation, a binary relation, a binary relation which denoted say by this sign is not less than, it is a notation for using the relation, okay, and satisfy a binary relation which satisfies the following, which satisfies the following conditions. Conditions. First condition is we will use the PO1, partially ordered relation. Condition 1 is a reflexive, that is reflexive condition, that is A is rated to A for every A belongs to M. Then second condition is the anti-symmetric. Anti-symmetric, that is if A is rated to B and B is rated to A, then A must be equal to B, that is anti-symmetric. And third is transitive. Transitive property is if A is rated to B and B is rated to C, then A must be rated to C. So, if these three conditions are satisfied, then we say the corresponding relation is a partially ordered relation or partial ordering. Okay. So, a set M together with the partial ordering is called the partially ordered set. Okay. Why partially? Partially emphasize that our set M may contain some element A B in which neither A is rated to B nor B is rated to A with the given relation. So, partially implies that partially emphasize that M may contain element A and B for which neither A is rated to B nor B is rated, and such an elements are called incomparable element. If M contains elements A and B for which neither A is rated to B nor V is rated to A, then A and B are set called incomparable element. Incomparable elements. And in contrast, if A and B are the two elements, they are called comparable if they satisfy either A rated to B or B is rated to A. Second, comparable. If two elements A and B are said to be in M, okay, in M are said to be comparable if either A is less than equal to B, A is rated to B, or B is rated to A, or maybe both. Let us see why. Why it is both. Suppose this depends on the relation in which the relation is defined. If I define the relation A is rated to B as A is equal to B, then both the relations satisfied. Okay. Say over the set of integer, if I define the relation A is rated to B if A is equal to B, then it will be a this condition, comparable condition is satisfied. Now, if there may be elements like this where none of them is true, either A is need not be rated to B or B need not be rated to A, then two elements are said to be incomparable elements. Okay. This type of means we cannot say always the two elements are rated. Okay. Say any two elements are rated. Suppose I say the relation A is rated to B if A divides B. Okay. Then it is not necessarily always the two element if we pick up, the one will be the divisor of the other. It is not all B is the divisor of A. Okay. It may not be possible always. Clear. So, this is what we are getting this. Okay. Clear. For example, 7 and 13, 7 neither divides 13 nor 13 divides 7, like that. So, it depends on the relation, and the correspondingly the set M will contain comparable or incomparable elements. Okay. Then we go for the totally ordered set. Totally ordered set or chain. A totally ordered chain or chain is a partially ordered set, such that such that every two element of the sets elements of the sets set are comparable For example, a partial order says that every two elements of the sets are comparable. For example, if I take set M as a set of integer of natural number, say suppose natural number, okay, and define the relation A is rated to B if A is strictly less than B. Okay. Then in this A is less than or equal to B. Okay. Then A is rated to B, this is rated to B if A is less than or equal to B. Okay. Then this is a partially ordered relation, because it is reflexive. Every element is equal to itself, so we can say every element is rated to A itself. If A is rated to B and B is rated to A, then A must be, means if A is less than or equal to B, B is less than or equal to A must be equal to B. It is transitive. If A is less than or equal to B, B is less than or equal to C, then A must be less than or equal to C. So, it is a relation. Then it is also a totally ordered set, because if I pick up any two arbitrary elements of this set, means two natural number, then one can always decide whether one is less than or equal to other, or one is greater than or equal to other. Means either A is less than or equal to B, or B is less than or equal to, will always be hold good. It means A is rated to B or B is rated to one of the condition will definitely hold. So, this will be a totally ordered set. Okay. Okay. Definitely. Then there is concept of upper bound and maximum element. Upper bound and maximum element. Okay. So, we say maximum element. Okay. An upper bound of a subset W, upper bound of a subset W of a partially ordered set M, partially ordered set M, PO set, partially ordered set M is an element U, is an element U belonging to M such that x is less than rated to U, x is less than equal to for every U, for every x belongs to W. Okay. For every M, depending on name U, U may or may not exist. Okay. Now, this is U may or may not exist depends on M as well as W. What type of the M and what type of W you are choosing, accordingly the max elements upper bound may or may not exist. Okay. For example, if I take this x is strictly less than U, say suppose all x is less than equal to U in an open interval, okay, or in the real line completely, then upper bound will not exist for it, because it will be the infinity, okay, like that. So, this will may or may not exist for that. Okay. Then a maximal element of M element of capital M, M is a partially ordered set, is an M belonging to capital M such that such that m is less than equal to x implies m must be equal to x. M must be equal to x. Okay. Then such a element is called the maximal element. Again, maximal element not exist, because if I take the real line example, say let m be the real set of all real numbers, be the set of all real numbers, and if I define the relation as x is related to y, if x is less than equal to y, then m is totally ordered set, totally ordered set, but m has no maximal element, but m has no maximal element. Okay? Because definition of maximal element says if m is less than equal to x, then m must be equal to x. Suppose I take any arbitrary number as a maximal element, and then if this is less than equal to x, it never implies, it may not imply that m equal to, because a number higher than this is possible on the real line. So, that is why it is not, maximal element may not exist. However, the maximal, in some case the maximal element may also exist. For example, this is a power set, let P x be the power set means set of all subsets of given S set X, of given set X. So, X is given set of all possible subsets of X means collection of all the subsets of X will give the power set of X. And let us introduce the relation, and let A is related to B if A is the subset of B. This is related to B, where A and B both are elements of the power set X. Okay. Then obviously, the P x is a partially ordered set, and in fact, it will be a totally partially ordered set. Okay. It is a partially ordered set, the only maximal element of this is a partially ordered. Take any two elements A B, either B, no, this is a partially ordered set, sorry, it is a partial ordered set, and its maximal elements, the maximal element will be our entire X. Okay. So, it has a maximal. We cannot say it is totally ordered partial, because if you take two elements, one is the singleton set 1 and the singleton set is 2, and you cannot say A is a subset of B or B is a subset of A. So, that is why it is only a partially ordered set is related to if A is a subset of B. Okay. If A is related to B means A is a subset, oh sorry, A is related to B means A is a subset, this is the condition is given. So, if we take the two elements A and B, one should be the subset of the other. Okay. So, X will be the, okay, that is clear. So, this is maximal element. Okay. Then let us see, these properties are again used and to prove this Jones lemma basically. So, Jones lemma what it says is, we will simply state the Jones lemma, because it is used in proving the Hahn-Banach theorem. Okay. The Jones lemma says let M, which is a non-empty set, be a partially ordered non-empty set, be a partially ordered set. Okay. Let M be a partially ordered set. Suppose that every chain, every chain C, I am going to C which is contained in M, every chain C which contained in M has an upper bound, this is content sign, okay, has an upper bound, this is C, upper bound, then M has at least one maximal element, at least one maximal elements. So, what this Jones lemma says is if M be a partially ordered set and which has a property that if I take any chain means totally ordered set, and chain is a totally ordered set, that is any two elements are always complement. So, if we choose a collection of the sets which is totally ordered set, then this chain has an upper bound, that is every chain there is an element x such that x is less than equal, such that all the elements are less than equal to x or related to x, then such a less than equal to x, then M will have at least one maximal element. That if every chain has an upper bound, then there is a guarantee that it will have an upper maximal element. Okay. In fact, the Jones lemma and axiom of choice, they are the same. The axiom of choice, what it says is that if suppose E is a set and we are considering a choice function from the power set of E to E, then pick up an element E from A, then the C of E will be an element of B. This is the choice function, okay, and the axiom follows from this Jones lemma and vice versa also. Okay. So, this axiom of choice and Jones lemma, they can be treated as equivalent things, okay, equivalent axioms. We are not interested in the choice of axiom, just we will see the Jones lemma. Okay. So, this is what we get. Now, Jones lemma itself has an application in proving the results of the functionalness. The first result is, which can be shown with the help of the Jones lemma, is we know that every vector space which is different from a singleton set 0 has a Hamel base. This we know, and it can be proved with very quickly with the help of the Jones lemma. Every vector space capital X which is different from a singleton set 0 has a Hamel base, has a Hamel Hamel basis. Okay. Proof. Hamel basis we know is X be a vector space, if V is a subset of X which is linearly dependent in span of V is over X, then we say V is a basis for that, it is called a algebraic basis or the Hamel basis for that. Okay. So, let us see the proof for that. Let us suppose M be the set of all linearly, it means every vector has a Hamel basis. So, there must be a linearly independent set which spans the X, okay, maximal elements. Let M be the set of all linearly independent subsets of X. Okay. Consider M be linearly independent subsets of X. Okay. Then we will see first that M is we can define a inclusion defined on a partial ordering only. Okay. So, since X is different from 0, it means there must be a non-zero element. So, it has, so there exists an element X which is different from 0 and in capital X, and this singleton set X will be an elements of M. M is the set of a linearly, this singleton set which is different from 0 will be linearly independent set. So, it will be the elements of M. Okay. So, that so this implies that M is non-empty. So, we are having a non-empty set of linearly independent subset of X. Okay. Let us define an inclusion relation. So, all such subsets are there. So, define inclusion relation on M, inclusion relation on M, that is two sets are there. A is rated to be, that is A is rated to be if A is a subset of B. This is our inclusion relation. So, this transfers the M to a partially ordered set. So, M with this relation is a partially ordered set. Okay. Now, we claim that this is also a totally ordered set. We claim that it is also a total, that is if I take every chain in this has an upper. So, every chain C which is a subset of M, that is if I take a partially ordered set, totally ordered partially ordered set in M, this is possible, because if you take the collection of the subsets, A is subset of B, B is subset of C like this, then take the union. So, that will becomes a chain. Okay. So, if we take a chain in C, one chain in C, then we claim that every chain, we claim that every chain C which is subset of this has an upper bound. Because again this possible, because the union of all subsets of X which are the elements of C, because the union of all subsets of C, all subsets of C are the elements of C. Okay. So, this is, so every chain has an upper bound. So, by Jones lemma, M has a maximum element, say V. Now, we claim that this V will be a Hamel base fold. Okay. We claim that V is a Hamel base for X. Okay. This is our claim, Hamel base for X. Okay. That is the span of V will be this. Okay. Let us suppose it is not true. So, suppose it is not true. Suppose it is not true. It means the span of B, that is span of V is not equal to X. It will be a proper subset of X. That is what is okay. So, it means there must be some Z. So, there is a Z belongs to X minus span of this, but minus span of B, minus span of B, is it not? Minus span of B, such that the B union Z would be linearly independent set containing B as proper subset. Proper subset, okay, which contradicts that B is a maximal element. B is maximal element. So, this contradiction shows that our assumption is wrong, the span of B will definitely equal to x. So, span of B is x. Therefore, the V will be a Hamel base. This proves. The similar type of results is also valid in case of inner product space. This we know in case of the Hilbert space inner product. That can also be proved with the help of John's lemma. The result is in every Hilbert space H, which is different from singleton set 0, there exists a total orthonormal set. Total orthonormal set. What is the total orthonormal set? We know the orthonormal set is a collection of these points where the inner product x y will be 0 if x is different from y and 1 if x equal to y. Then this is called the orthonormal sets. Okay. And whenever the set this is orthonormal. Okay. What is the total orthonormal set? A subset M, when the closure of the span M is x, then we say it is a total orthonormal set, is it not? Then in fact, this we have defined this thing as like this, that M is total if the closure of the span of M is x. So, this we want in Hilbert space there exists a total orthonormal set, that closure of the span of M will be H itself. Okay. So, let M be a proof, again the proof follows on the same line. Let M be the set of all orthonormal subsets of H, set of all orthonormal subsets of H, orthonormal subsets of H. Now, since H is not equal to 0, so this shows it has an element x which is different from 0. Okay, because H is not equal to 0. So, there will be an element x which is different from, and the corresponding orthonormal subset of H and the orthonormal subset and an orthonormal subset of H and an orthonormal subset of H is this y, where y is equal to x over norm x. So, that the norm of y becomes 1. Okay. So, this will be, now this implies that M is not equal to phi, M is non-empty set of orthonormal subsets we have chosen, and because of this condition M becomes non-empty. Okay. Now, let us consider the set inclusion defines a partial on M, define set inclusion relation. So, M becomes a partially ordered set. So, M is a partially ordered set. So, this gives M a partially ordered set. Okay. Now, let us pick up a chain. So, let us consider a chain, then this chain will have a upper bound. Picked up this chain, pick a chain that is totally ordered set, pick a chain C, which is subset of M. Now, this C will have an upper bound. This C, now this every chain, now this will have an upper bound, because why it will have an upper bound? Because the union of all subsets of X which are the elements of C, because union of all subsets of X are the elements of C, which are elements of 3. This is upper bound because union of all subsets of X is again in X. Okay. So, as an upper bound C, because it is the union of upper bound C all subsets of X, this okay. As an upper bound, because it is the union of all subsets of X in C. Okay. Because it is means C is a set, consider the union of all subsets of C, then this will give the upper bound for it. Okay. So, this is a upper bound for this. Now, why John's lemma? This M will have n maximal elements. So, John's lemma, M will have a maximal element, say F, and will have a maximal element say F. Okay. Now, B proved F is a total. B prove now F is total in H. Then our result is complete. Suppose it is not true. Suppose F is not total. Suppose F is not total in H. Now, there is one result, that if a set F is total in H, then there will not be exist any non-zero X which is orthogonal to every element of F. So, when you say F is not total in A, it means there must exist a non-zero elements in F which is orthogonal to each element of this. So, we can enlarge the F. So, what we create? So, there exists a non-zero Z belonging to H such that Z is orthogonal to F. This is by the result which we have proved already, that a set is total if and only if there exists no non-zero element exists which is orthogonal to this, or X belongs to orthogonal implies X must be 0. Okay. That is what we have shown that result. So, according to there will be a non-zero Z which is orthogonal to F. It means we can take F1 as F union E, where the E is Z over non Z, and since Z is orthogonal to A, so F1 will be now a orthonormal set. Okay. This will be orthonormal. F1 will be orthonormal set which covers or which contains F as a subset. So, this is as a proper subset rather than not exactly proper subset. It means F cannot be maximal if it is so. So, M is not total in H. So, this contradicts the maximality of F. So, F cannot be maximal element. F cannot be maximal element. Therefore, a contradiction shows that f is total, that f is total in H. That proves the result. Okay. So, this is one. Now, there is one more concepts are which we know, lattice. Okay. Now, lattice that may also be used something. What is the lattice? A lattice is a partially ordered set. A lattice is a partially ordered set M such that any two elements x and y of M have a greatest lower bound we write it as denote it by x meet by and a least upper bound denoted as x joined by. So, a lattice is a partially ordered set in which if we take any two element of this, then the meet and join they must be the elements of M. Then such a partially ordered set is called the lattice. Okay. For example, if we take x to be P x as a power set of x, and let us define the ordering as the subset A is less than or equal to B if A is a subset of B. Then the meet and join both are available. Then obviously, the meet is A, B is A intersection B, while the A join B is the A union B. Okay. So, this meet and join are available. So, it will be a lattice for this. Okay, thank you. That is all. So, we will discuss next time the remaining. Okay, thanks.